So today we're going to be talking about the specific species within an aqueous solution and how to find the concentrations of those species. So I wrote out an example problem we can go over. This says for a 0.0359 big M aqueous solution of cyanic acid, HCNO, determine the species present and their concentrations, and then it gives us the Ka value. I went ahead and wrote out the equilibrium equation. We already know that cyanic acid is a weak acid, but if you didn't, you would look at your hydrogens in each of the compounds. So here on the product side, we have our weak acid, and it has a hydrogen at the beginning of the compound. And you go over to the reactant side, that hydrogen is no longer there. We know that acids donate a hydrogen, so we know that since we no longer have a hydrogen over here, that this is an acid. It's our weak acid. And this compound over here, what is left over after we take away that hydrogen, is what we call our conjugate base. And this is water. It's a liquid. We won't include that in our calculations because we only include aqueous or gas, no solids or liquids. So this compound right here is our hydronium ions, which are important when you're trying to find the pH of an aqueous solution. So now let's go over how to find the concentrations of each of these compounds. So we know that Ka is equal to the reactant side, so our CNO minus multiplied by our hydronium ions. So we will multiply what is on the reactant side, which is our conjugate base and our hydronium ions, and then we will divide that by what is on the product side. And the product side, we're only going to include that weak acid because our liquids do not go into our equations. So it will be our cyanic acid. So from here, we're going to go ahead and do our ice table. In our initial concentrations, and in the problem, it gives us our initial concentration of our cyanic acid, which is 0.0359 big M. And for our conjugate base, that is unknown, and same with our hydronium ions, so we will give those a value of 0. And then our change, we know we're going to take something away from this in order to get our conjugate base. So we're going to give it a negative x value, and we're going to give these x, and these will be the same. So our ending will be 0.0359. Oops, I wrote that opposite, 359 minus x, and these will be x. So now that we have these values here, we can go ahead and set up our equation. So Ka is equal to x times x divided by 0.0359 minus x. So here is when we have the question of simplification. So we know that here, let me write it out with our concentration. So our Ka value is 3.5 times 10 to the negative 4 is equal to x squared over 0.0359 minus x. So for simplification, we know that if these values are 1,000-fold difference or more, then we can simplify this negative x here in the denominator. So if I write out this 3.59 times 10 to the negative 4, that would be 0.00035. And we can tell that this is 1,000-fold difference because if we move it over 3 places, we are still a lot greater than this problem. So it's more than 1,000-fold difference, so we can go ahead and simplify and cross out this x. So we now have, all right, a new color here, 3.5 times 10 to the negative 4 is equal to x squared times 0.0359. So now we're going to bring our calculator here, and we'll take 3.5 times 10 to the negative 4. Multiply that by our denominator. We're going to multiply each side by this. So 0.0359. So we are now going to get 1.2565 times 10 to the negative 5 is equal to x squared. So we're now going to take the square root of x. And our x value will be 3.54 times 10 to the negative 3. So now we're going to come back up to our ice table and see how that correlates. So we see our x's are what's in the reactant. So it's going to be our conjugate base and our hydronium ions. So this is equal to H3O and CNO minus. And then in the equation, we already had the concentration of our weak acid, and that's 0.0359. So I know I was just going to show you the concentrations, but I'll go ahead and show you how to get the pH of this problem as well. So your pH is going to equal negative log times your hydronium ions. So we solved for our hydronium ions, and it is 3.54 times 10 to the negative 3. So we'll plug that in our calculator. Negative log 3.54 times 10 to the negative 3. And we get a pH of 2.45. That makes sense because the more less than 7 you are, the more acidic you are. We know that cyanic acid is acidic, obviously, so we're expecting a acidic pH.